So the last speaker today is Lucas Mann, who will tell us about quasicoherent sheaves and the relative Fargues-Fontaine curve.
Right, yeah, so thanks a lot for the invitation and for the introduction. Right, so as the title says, I want to talk about some notion of quasicoherent sheaves on the relative Fargues-Fontaine curve. But before I do that, I'll start with some motivation, which does not involve any of these two notions. Okay, say you pick your favorite non-Archimedean field over QP. Then you pick your favorite smooth rigid variety over that. Over K, and let's assume it has pure dimension D. And say you also pick your favorite p-adic coefficient ring. And well, I'll use a slightly fancy word here, but so it's a nuclear module over ZP, and by nuclear I mean roughly in Banach. Okay, so it's a term coming from condensed mathematics, ZP algebra. And if you don't like these fancy words, I guess you can take lambda either ZP, FP, QP, QP bar, CP, or whatever you want. Okay. And so if I have such a nuclear ZP algebra, this induces a pro-étale sheaf. Sheaf, which I'll also just call lambda on X. Okay, I mean, I guess it's clear how I define this. I just sent a U to, well, let's say continuous functions of the topological space underlying U for lambda. And let me pick one more data, namely a local system. On the pro-étale side of X. Okay, and in this setting, I guess one of the basic questions of p-adic cohomology theories is, what can I say about the cohomology of L on X? And in particular, is there some sort of functoriality for that cohomology? So let me maybe phrase this as a conjecture, even though part of the conjecture is a construction, which is also conjectured. So the conjecture is there's a good notion of pro-étale homology with compact support. And we'll just call this gamma C X and L. So note that I don't write an R here, and I tend to not write R's for derived stuff. Everything is derived for me anyway. So we have such a cohomology theory, and then there should be a pairing, or maybe let's just call it a map. So some sort of concretuality map going from the pro-étale cohomology, or maybe I should. So this is literally just good old pro-étale cohomology of L. Sorry, maybe here I take L dual and I shift it by 2D. Maybe I take this also by D. And then I tensor this with this cohomology with compact support of L. Right. So there should be some sort of map like this, inducing an equivalence an isomorphism.
Sorry, on the left-hand side.
Yes, I will explicitly not say that now. But you need to be careful, of course, of what exactly you mean by this. But so I want this to be, well, pairing, perhaps not a perfect pairing in the sense that each of these are the dual of the other, but I want one of them to be the dual of the other. So I want gamma x L 2D D to be isomorphic to, or let's just say, the dual of gamma C X L. Okay, and if I phrase it like that, I guess the statement is somewhat empty because I guess, okay, maybe not completely empty, but I guess to satisfy this, you can just try to find anything such that the dual of that is that one. But of course, that will not help much, right? So the point of this conjecture is that there should be a good notion of cohomology with complex support. And
so the shifts are still D even in the arithmetic case?
yeah, yes, well, you're careful with what you mean by cohomology, I guess. I mean, for me, that would be by cohomology, I guess, I mean the push forward decay. And yeah, of course, in the arithmetic case, of course, there's some direction, and you would not want to take the cohomology of that as well, because then, of course, there's some additional.
Finite dimensional vector systems, lambda modules.
No, though they are infinite dimensional.
So what is the dual here?
Yeah, I will come to that.
Okay.
Let me maybe first say something about the current progress of this. So I guess the easiest case you can consider is suppose that lambda is p torsion, or some torsion. Okay, so now we end up with essentially a question about a p cohomology. And then in this case, even then in this case, this is not an easy statement, but it has been solved both by me and by Bogdan and Gaba. Last year. Okay, and also from the p torsion case, you can deduce if X is proper. And then lambda arbitrary. But the local system, let's say it's just lambda, then you can reduce this, follows from the previous case. Yeah, because if X is proper, well, first of all, if you have it for mod P, then you can get to ZP, I guess, by just taking limits. And if you have it for ZP and you are proper, then you can also pull out colimits, so you end up with QP and basically everything. Okay.
In the first case, X, there's no restriction on that.
Oh. Here it is. X is proper. Okay, so basically this leaves us with two important cases. The first one is that the local system is not trivial. And the second one is that the space is not proper, but only maybe Stein or partially proper or something like this, or I mean, maybe even completely general, okay? And the second case has been solved, at least in the Stein case, by Stein. And the local system is just lambda, or maybe, I don't know, should we say, let's say lambda is QP, and the local system is also QP, which I guess is the relevant case here. And then this conjecture was established by Colmez-Gilles and Niziol. Well, at least they announced it, and they allowed me to state it like that. Okay, it's a little bit semi-announced. Okay, and Right, so one thing that's still open as far as I know is that if L is arbitrary, even if X is proper and L is some QP local system which does not come from a ZP local system, some weird stuff happens and it's not so clear what to do. Okay, and now let me finally maybe say a little bit about Elaine's question on what exactly I mean by this, right? So we need to be very careful with this. So unless X is proper and L is lambda, one needs to be careful. In which category? One works. I guess naively you could try to just work with lambda modules. I guess one very quickly notices that that is far too naive, because if X is not proper, these things tend to be infinite dimensional. And then there's basically no hope that you can get nice statements for infinite dimensional things. Okay, so then the next thing you can try is you can try to put some topology on these things. Okay, and then you can hope if you take topological duals here, that you get a nice statement and maybe completed some sort of completed tensor products here. But unfortunately, not even that is enough. So here's one computation that I want to quickly sketch, also by these three guys. So X is the open unit disk just of dimension 1. Then Colmez-Gilles-Niziol computed. So you can compute the cohomology, pro-étale QP cohomology of this thing, and you end up with, I guess the first one is easy, it's just QP. The second one is the global sections of the disk modulo, let's say K is CP. The second one is global sections of the disk modulo CP. And from there on, it's just 0. And if you look at the cohomological complex support, now you might object that part of the conjecture is defining this, but they have a definition, at least in this case, a good definition of what this would mean, and they can compute it. And this one is computed as QP direct sum functions on the boundary of X, modulo functions on X, if X, if I is 2, and 0 otherwise. Okay, and then what they noticed is if you want any chance of there to be in duality between these two things, you need to be a bit careful, because this QP looks very dual to this QP as a duality over QP. But this guy here, and this looks also dual to this guy here under some form of coherent duality maybe. But then the dual to which you have to hum to, or the dualizing object to which you have to hum to is CP and not QP. So you seem to mix two different notions of duality here. And also the degrees don't really seem to match. Like this duality happens in degree 1 and this happens in degree 2 or something. Okay, but they managed to solve this by introducing a category of vector spaces, which I will say something about in a second. And the goal of our project, of our joint work, is solve the conjecture in full generality. And what could that mean? Well, to me, this means by providing a six-functor formalism. Full six-functor formalism. So what do I want to any x? I want to associate some category, maybe. So to every x, I want to associate some category d of x comma lambda, for which I want to have the six-functor formalism, and then this should satisfy some properties. Well, first of all, I want to have a six-functor formalism, but I also want to be able to compare it to maybe some more naive things you could try. So it should embed, or at least, well, let's say, at least have a map to just the category of V sheaves of lambda modules on X, which is this category vector spaces. Okay, maybe they only consider it over QP, but I guess you can do it over any lambda. So that's this category vector spaces in which they form these dualities and show that they actually work, at least in the Stein case. And of course, I also want to have some, let's say, fully faithful embedding of some nice formal sheaves. Let me maybe put here d nuke x lambda. So by this, I mean something like int Anna lambda sheaves on the pro-étale set. Okay, so basically everything you can construct out of hand should land in here, maybe, or maybe let's say over convergence. So for example, this contains the local systems L. So you have some way of mapping the nice ones into here. You have a six-functor formalism here. This will do some crazy stuff to your things, which might end up with some non-trivial vector spaces, which you cannot represent in here anymore, like in the usual nice category of sheets. But at least you have a concrete duality, and you should have a very explicit, well, roughly explicit description of what these things are. And so our guess for what we can take here, and that is the reason of the title of the talk, is what we take here is we take quasi-coherent solid modules over the ring OX plus tensor over ZP lambda on the Fargues-Fontaine curve over the relative Fargues-Fontaine curve over X.
So when you talk about BS lambda, they horizontally, so to speak, they have no topology.
What is non-topology?
BS, your BS is not topological BS, it is arbitrary BS.
Well, I just take V sheaves on X. Isn't that what you define? Maybe I was wrong then. But I mean, lambda is a topological ring. And any topological module, of course, embeds into that. But okay.
Dual is something a bit different.
Oops, sorry. Well, I guess, anyways, this guy will embed into this, hopefully. Okay, and so with this motivation, I will basically not talk much more about this setting. So the rest of the talk, I will talk about what the hell this means here. So basically today, or I mean, that's also the current state of what we have. We construct this category. Okay. So before I can talk about quasi-coherent sheaves on the Fargues-Fontaine curve, maybe I should talk about what kind of quasi-coherent sheaves I mean here, because they certainly should have some sort of topology on them, because all of these things are topological rings, right? So let me first do something which is completely independent of p-adic geometry. And just talk about adic rings and descent modules along those. Okay, so if I want to talk about descent for adic rings, maybe I should first say what I mean by an adic ring, but I guess it's more or less the obvious version, maybe with a slight twist if you're not used to this condensed stuff. But for me, an adic ring is always a condensed and animated, essentially animated ring. So condensed roughly means topological. Animated means something like derived. But don't worry too much about the derived stuff because the rings we care about at the end, they're not derived anyway. So a condensed animated ring A is adic. If there's some finitely generated ideal, so if it has a finitely generated ideal I, such that A mod I is discrete, and A is I-adically complete. Okay, so I guess it's more or less the obvious notion of what an adic ring should be.
Sorry, what do you mean by finite generated ideal? I mean, because you are in this definitive.
Well, I guess you can take finite generated ideal and pi 0 of A.
And also take point, right? I mean, because it's a condensed structure.
Yes, pi 0 of A of star. Yeah. And also you should be careful with ideal. I guess whenever I say ideal, I essentially just mean a collection of elements. And when I write ideal to some power, I guess that just means the same collection where I raise every element to the power. I don't actually take the ideal to the power. But usually that doesn't matter because I take limits over these powers anyway. So
Sorry, how do you quotient by this thing? This ideal.
maybe just ignore the animated stuff. I mean, okay, if I choose a bunch of elements in A, that gives me a map from Z adjoint x1 blah 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 xn to A. And then I just tensor over that thing with Z, quotient all the things, and that's not a condition. Okay, but don't worry too much about this animated stuff. It works in the general setting, and well, for the general statements of descent, it's crucial that you allow this because you really need, if you form fiber products or tensor products of these rings, in general, you need to be careful with taking really the derived ones, otherwise things might might not work. But unfortunately, in our case, everything is not animated anyway, so doesn't matter too much. So then,
Yeah, this completeness includes separatedness as well. I-adic.
yeah, I mean, it literally just means that A is the limit of A mod I to the n.
But then if you take like the R-lim or something, then
It is automatically an R then, yes. And it's derived complete. Derived I.
I thought there was like separatedness is a separate condition.
Sorry. So what I mean is derived I-adically complete. I guess maybe this does not imply separateness, yes.
So you include that in your definition, separatedness.
No, I mean, I only require that A is the limit over A mod I to the n in the derived sense. But in practice, I guess, I mean, the rings I plug into this are, well, I don't know, structure sheaves of Fargues-Fontaine curves, and they always have all the nice properties you want to have. So, okay, so for an adic ring A, we denote solid hat of A, the category of completed solid modules, and I don't know, and maybe I'll just use this notion A solid hat modules. And I do not want to assume that people know solid stuff too much. So I will probably, I don't want to properly define what I mean by this category, but rather try to give you some intuition of what it is. So first of all, I mean, the basic intuition of this is that this is, you should think of this as some sort of complete topological A modules. And okay, maybe complete is a very bad word here, because I certainly do not mean I-adically complete. This category certainly contains arbitrary colimit is adiabatic conform. So okay, maybe take this with a grain of salt. So for example, you can contain any infinite A module that's inside of this. And more formally, this category is compactly generated by the elements A S solid S, which are, by definition, you take the colimit over all finite type algebras inside of A, and for each that you take a limit of that thing A prime is I, and then you I-adically complete, and therefore as any profinite set. Okay, maybe this looks a bit weird. If you know condensed stuff, then this might look much less weird to you. So maybe let me, for those people who know condensed stuff, say roughly how this relates to what we used to. Because I do one thing here. I take this I-adic completion, which is something that you do not do in condensed stuff usually. So let me make a remark. Namely that there's a forgetful functor D solid A, D solid hat A to D solid A. So this is the usual thing that Clausen also defined. The thing I define is well, somehow slightly larger, I guess. I mean, it has some more structure. This thing will not be fully faithful. But you still have all the nice properties. So this category has a tensor G structure all limits and colimits and so on.
Sorry, what's that colimit index again? A prime. Like, what is A prime? Is it?
Sorry, yeah, I should have said that. So that's the finite type over Z, I guess.
Again, like a condensed animated.
Yeah, I guess you write A, if A is an animated ring, I guess you write it as colimit of whatever, shifted colimit of finite type things over Z or something, and yeah.
Okay. This is something in the condensed world. It's
yeah, this is a common construction, the condensed world. I mean, this is common. This I-adic completion here, this is not common. I mean, this is not what Clausen also do. We were forced to do that. I mean, we tried really hard not to do that, but we were forced. And the cool thing, I mean, this really helps because if I take this, then every element in this category is a colimit of I-adically complete stuff, and that is wrong in this category. And this is really, 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 really annoying in this category. So even if A is I-adically complete, the modules in here might not be made out of I-adically complete stuff.
Wait, if A is animated, what is the precise collection of A prime?
Well, I guess you can always write any animated ring as a shifted colimit of finite type rings over Z, right? Yes, as a discrete ring, maybe, not the animated structure. But since you take I-adic completion at the end, I guess you don't have to care about the condensed structure.
And sorry, you made some comment about putting complete in parentheses. You said you shouldn't think of this as I-adically complete. I mean, but I guess you're saying this category is generated by things that are
right. So it's generated by things that are I-adically complete, but the objects themselves are not I-adically complete, and that's crucial. I mean, I could also just take all I-adically complete A modules, and that will certainly embed fully faithfully into this. But I have something more, right? I can also take whole limits of these things. And that's important because, for example, I mean, if I is just P, just generated by a single element P, then in here I can consider A adjoint 1 over P. So for example, if A is ZP, I can, QP is a very valid element in here. Okay. So this is really some sort of quasi-coherent sheaves, which are not necessarily I-adically complete. They're just stuff that you can make out of I-adically complete things.
So that first colimit is sifted but not filtered, or?
I guess in full generality, yeah. I guess you can also ignore the animated stuff, which is just a static ring first, and then take the induced analytic ring structure if you want.
I mean, you can pick one choice, this colimit, and then use that for everything. Or I take all of the different ones I can.
It's not, yeah, it doesn't matter. I mean, any choice of colimit will get the same result. The reason why this colimit, this weird colimit, I mean, you could also just try to do it directly with this, right? And but the reason why I have this colimit is that I don't know, if I have a big map of these of rings, if I have a map of adic rings, which is very big, not a finite type or anything, then it's really useful that everything is induced from finite type steps so that I can pull arguments through. Okay.
So these are like the compact projective objects, or?
These ones, yeah, yeah.
And then you just freely generate.
More or less,
Yeah.
yes. Okay, and so here's a little lemma that maybe tells that the things we're doing and this category might be the right one, because I mean, for a long time I was very worried that I chose this category, right? I mean, Justin 1000 and Peter Scholzer had a reason to do that one, and now I propose to choose that one instead. But it has some nice properties that the other one doesn't have. And so here's one, namely the tensor product. This preserves right bounded I-adically complete I-adic completeness. So if you have two right bounded complexes which are I-adically complete, the tensor product will again be I-adically complete. So this tensor product is some sort of completed tensor product. Also, for an adic map, F from A to B, there's a base change functor. It's just the left adjoint to the forgetful functor. So it goes from A modules to B modules. Oh, sorry, I used two different notations here. Exists and preserves right bounded I-adically completeness. Right bounded I completeness. Okay, so you have these kind of nice properties, and I think they are wrong for the definition of Clausen-Schulze. So if you want, well, if you want at the end, I want to reduce everything to I-complete stuff because I want to reduce mod I. So if you want to do these kinds of arguments, this category is really better, much better suited somehow. Okay, so I want to talk about descent because I want to define this category, which is somewhere written over there. And the crucial input that I need in order to get a good definition of this category is some descent result for sheaves for the objects in that category. So maybe let me first phrase what I mean in general by that in this abstract setup. So we say that modules descend along an adic map from A to B if well, you have a map from B solid of A to the limit over n and delta of B solid hat of B tensored over A completed dot A completed B. And I guess this is n plus 1 times, and I want this to be an equivalence. Okay, so if you're not so used to this infinity categorical stuff, roughly what's written here is descent data of this map A to B, right? I mean, an object in here consists of a B module together with some isomorphism of its two callbacks to B tensor B, together with a co-cycle condition. But since we're infinity categorical, this co-cycle condition is another homotopy, and you end up with more and more homotopies and so on. But really, this is just the usual notion of descent data. Okay, and basically, what I'm interested in is for what kind of maps do you know that this descent holds? Because once I know that, yeah, we'll see at the end why that's so crucial to understand this category. And so here's a theorem, just in this abstract setup, namely that suppose we have an adic map such that there is some integer d, such that for all n, the map A mod I to the n solid to B mod I to the n solid is descendable of index less or equal to D. And okay, I will not write formally what this means. I'll give you the most important example of descendability in a second. But basically, descendability condition is much strong. I mean, it implies this, but it's much stronger. It says that it not only satisfies descent, but due to a very strong reason, basically. And the index is some of the complexity of the descent. And if that is true, then modules descend from a solid hat to B solid hat. Maybe I should also write solid hats here, sorry. Okay, so that is the main criterion I have for proving descendability. And I mean, what you should read here is if I can show that I have descent modulo all I, modulo all I to the n, then I have descent. And this might sound very reasonable at first because you think of modules over this thing as being some sort of I-complete modules. But recall that the modules I consider here are not just I-complete ones, they're also columns of I-complete ones, right? And once you take that into account, it's maybe a bit more surprising that you can actually get descent like this, just out of the descent mod all to the I to the n. Because in particular, in here, I can invert an arbitrary element and I will still have descent, right? I mean, if I is something like P, and I have this descent, and I can also invert P and I will still have descent of modules along the rings with P inverted.
Sorry, Lucas, the limits in the box hat can be computed in condensed A modules?
Yeah, but this, I mean, this is a Fargues-Fontaine function with all the properties you would expect. Preserves limits, co-limits.
Analytic ring structure on A.
No, that would require this to be fully faithful.
Okay.
It is up to the fact that this is not fully faithful.
And, can I ask, so index D, you said you don't expand now, but the D is like an upper bound,
Yes.
which is true for all powers of I? Or?
Right, right. So for each power of I, you need to check it's descendable, and you need there to be an upper bound on the complexity somehow.
Independently of the
Independent of the n.
power. Yeah.
Yeah, right.
Okay. So
And the idea is roughly that if you want to descend along this map, you descend along all I to the n, along mod all I to the n, and if the complexity of the descent is bounded, then okay, that's the rough intuition. Yeah.
So do you know that it's also descendable, like not more than only that modules descend?
Yeah, it is right. For the correct notion of descendable is also descendable. I mean, it is descendable of index less than or equal to 2D. Yeah. Yeah.
Can we expect one of the two functors the other way to be fully faithful? Also not.
I mean here? Or?
Yeah.
A functor from here to here? No. No.
Also not. Okay.
No, I think.
I think you have the fear that this functor is conservative, right?
This functor is conservative. Yes.
Ah, okay.
I mean, it really is a forgetful functor. You should really think of this as a ring over this. Except that you cannot model that ring in the usual condensed framework. But I mean, as a monad, it's okay. I mean, you can define this as modules over some monad, which is actually the monad that you get out of I completion of the monads of this monad. So this is the monad that is the I completion of this monad, and then you take modules over that. And that is fancy categorical speech for what's happening there. Okay, here's the corollary. That's the one that I'm mostly interested in. Namely, suppose B can be written as a completed colimit of some BIs such that all A to BI are mod I to the n, so such that all A mod I to the n to BI mod I to the n are Fppf, then modules descend. Say again? Arbitrary. I mean, if you take a countable one, then it's even descendable, but I don't care. Oh yeah, filtered, of course. Yeah, sorry. Yeah, thanks. Okay, and the key input is that Fppf maps are descendable index less than or equal to 2. And I think the first one who observed it and wrote it that way, Matthew. Although he didn't write it in the setting, not in the solid word, but right, I mean, the basic idea is the same. Okay, so in particular, if you take any adically in Fppf map, you have descent of modules over there along that map, but also after inverting arbitrary elements, you still have descent, and I don't know. You have as much descent as you can hope once if you start with such kind of map.
So if you start with a p-adic formal thing, which kind of generic fiber do you get?
Well, I mean, if it is a p-complete thing and you invert p, I guess you get the rigid fiber. I mean, do you allow some formal variables? Then of course you get something weird.
Well, I mean, but there's something in here that I can take sort of. What can I take?
You can take your favorite formal scheme, I guess.
I mean, invert p, and then I have some topological gadget.
I guess.
Yeah. But there are sort of lots of topological gadgets that arise that. I'm just wondering if it's the same as.
Yeah, I guess so. I guess these kinds of, I don't know much about these kinds of descent results. I mean, probably this exact result has not been in the literature before because no one defined that category before.
No, that's what I'm
but,
sort of, when I look at familiar things in that category, like.
Right, I mean, you can, for example, look at just descent of perfect complexes over these rings, and I guess there are results like that in the literature. And of course, this in particular implies descent of perfect complexes along this map or any map you can get out of this by a base change.
But I guess so your argument is really, if I'm looking at like adically complete things, this is somehow the best category to take.
That is my impression, yes. Yeah. Well, based on the fact that it seems to work.
Yeah.
Okay, how far is the theorem from the same statement without any topologies? Like without any contestants?
What would be the statement then? Just for I-complete modules? Or?
No, it's, you have a map A to B of, let's say, I-complete rings, and mod I to the n is descendable of uniform index, and A to B is descendable of the same index, just for the ordinary commutative rings.
I don't think that's true, but I don't know. Yeah, I think, I mean, I haven't thought about it. But I would guess that the tutorial is very useful here. Okay, yeah, sorry. I mean, of course, from this descent, you get also descent of nuclear modules over that, or maybe discrete modules over that. You also have some sort of descent notion of that, but you need to be very careful, of course, because these base changes are topological base changes. You can plug in a discrete module, but what you end up with might not be discrete or something like that. Okay.
So I have faithfully flat map of rings without finite descent. Descendable as well of some index.
No, I mean, I don't know, but not as far as, I mean, I don't know any proof of that. In Fppf is the best I can do.
Does it use Fppf or just countable generation?
I think it really uses Fppf. I mean, I have to reduce to a setting where I'm a finite type over C. I mean, the idea of this proof is I go to, well, if I have an Fppf map, then I can, without loss of generality, it comes from by wire base change from an Fppf map of finite type things over Z. And in that case, the solid stuff is particularly nice. And that's why I need it. If you ignore the solid stuff, then yeah, countably generated, I guess, as you know. But if you want to work with the solid stuff.
Descendable doesn't have the usual meaning. It's self-descendant.
I mean, yeah, it has. I mean it in some sense, in some kind of condensed meaning. Yes.
Perhaps that one descendable of index bounding.
Organize what one?
Well, what does it mean? Descendable of index.
Maybe we can discuss this at the end because I want to talk about perfected spaces as well. Sorry.
But you're saying FPQC maps are not?
Yes. It's kind of a miracle that this works. I don't know how Akil noticed this, but yeah. Okay.
No, maybe I missed the point. So you mentioned, you mean that descendable for modules is the same as descendable for solid modules or not?
No, it's not the same. Descent for solid modules is a priori much stronger.
Much stronger, but what about if you restrict the light setting? It doesn't help.
It's still stronger. I mean, for discrete modules, you have FPQC descent, and I'm not aware of any FPQC descent statement for solid modules. And Fppf is kind of the best I can do. Okay, so why do I care about perfected spaces? So let's maybe get back to the category, like to the original goal, right? So the basic idea of defining this category dx lambda. Well, it's hard to define it directly on any rigid variety, but it helps a lot if I make my rigid variety easier by passing to a perfectoid cover. So we pick a perfectoid cover. X tilde to X, then define d of X tilde comma lambda. Now, in the perfectoid setting, there's an actual good meaning of the relative Fargues-Fontaine curve, so there's a good hope that this might work. And then descend along this cover. Okay, and the hard part about this recipe is this descent, because if I want to descend along this cover, I should better check that on perfectoid spaces, the category I define here satisfies descent, because otherwise there's no good notion of descending to anything. Okay, so the main goal is proving as much descent as possible on perfectoid spaces. So here's the definition. When we first introduce some notation, so I consider the category perf df, which is the category of finite perfectoid spaces.
Do you need descent or hyper descent?
Well, a priori, I guess you can choose a pro-étale cover and then descent would be enough, but I prove hyper descent anyway.
No, but I mean, when you take iterated subproduct to.
Well, I mean, if you know that the check nerve consists of perfectoid stuff, then well, if it's pro-étale, I guess you can. I don't know, take it strictly to the disconnected pro-étale cover, blah, blah, blah. It would be enough if you have a pro-étale cover. For V covers, no, but I prove hyper descent anyway, so it's okay. So this is the category of perfectoid spaces over the T. And this category is equipped with the V side, where the covers are essentially just vector maps. Yeah, this is not better. I feel like I'm too tall for this. So I'll stick with this. Okay. Then here's the theorem. How much time do I have? 10 minutes. Okay. Let me first state the first theorem. So, okay, you could now hope to define some sort of category of quasicoherent sheaves on these perfectoid spaces, and you can hope that this satisfies descent. And yeah, the result is the following. There is a necessarily unique hypercomplete V sheaf of infinity categories. Going from this category curve F up to infinity categories. I prefer to write it just like that, but you can also put an infinity if you want. So it sends an X to some category which I will call the solid head of X plus. And so I need to specify something to make it unique, such that on totally disconnected X equals RAA plus. And the totally disconnected perfectoid spaces, they're particularly nice ones. They essentially just a profinite collection of geometric points or perfectoid points. In this case, we have that this D solid hat A OX plus is D solid hat A plus. And this little a here means almost. So I invert all maps which are almost isomorphisms, and I will not say more about this. If you don't know what it means, just ignore it. It's a minor thing that always appears in this almost mathematics. I mean, it originally came from Faltings, and it's really useful here because otherwise the plus rings don't behave as well as you might hope. Okay.
It's just with respect to the p-adic topology.
The hat is yes, yeah. I mean, you have a study. I mean, this is an adic ring, right?
Just for p.
Well, it can live in characteristic p, and then it's, I guess, pi. But yeah, if it lives in characteristic 0, you can take p, and then this is just p-adic complete. Okay, and so this result we had on a conference in Bonn where I gave a similar talk, and now I want to extend this. So it's nice because these totally disconnected spaces, they form a basis of the pro-étale side, which is somewhat miraculous because they are extremely simple. But if you want to do actual computations, and in particular, if you want to show descent on the Fargues-Fontaine curve, it's really helpful if you have more descent than this. So here's the final descent. I wanted to at least sketch the proof of this. Because the actual proof is a 3-long vastly technical computation, but the idea is that the V covers of totally disconnected spaces are essentially in Fppf. Okay, and this essentially is to make sense of this. Essentially, you have to work with it, but that's roughly the idea because it's just a collection of valuation rings essentially on the plus rings, and on valuation rings you're very easily into Fppf. Okay, and so how do we extend this? Well, in my thesis, I introduced a notion which I call fast bounded. So let me maybe very quickly introduce this here. I say a map of finite perfectoid spaces is fast bounded. if the following is true, so let me check here because, okay, so first of all, it has finite transcendence degree. Let's pull this thing up. Okay, and then for some pseudo-uniformizer phi on X, the map or the functor, I'll just call it F lower star, going from, okay, now I have to cheat a little bit because I technically didn't introduce the category, so I will write here now, but maybe you can roughly guess what I mean. That's finite cohomological dimension. Okay, so this category here, that I write here, is roughly the thing that I have here with mod pi, where it's just mod out by pi. And then I write comma z, and this comma z means that in these generators, I make things a bit simpler. By basically just taking the same, where I just take a z here, and then I tensor this thing up with my ring. But yeah, don't worry too much about that. It's a slightly technical condition, which roughly says, well, you should think of this as F has finite cohomological dimension. And we say that X or Y is plus bounded if Y has, the tilt of Y has a plus bounded map some totally disconnected space. Okay, so this notion appeared in my thesis because, well, these cohomological boundedness conditions, they're very useful if you want to define six factors, because they give you a good handle of what the lower Schwick functor will do. But there's another good property of this. Maybe, okay, this is just some abstract thing, but let me give two examples, namely weakly perfectly finite type maps. Are class-bounded, and also pro-étale maps are also class-bounded. Okay, so it's easy to see that this condition is stable under composition. So in particular, anything you can build out of these two cases is class-bounded. So in particular, any space is weakly of perfectly finite type over something totally disconnected, and maybe you've thrown some pro-étale stuff, is also class-bounded. And the main result we have so far in constructing the category, and this will really enable us to construct the category, is that if X is class-bounded, then this category that I defined of quasi-coherent OX plus modules is really just a category of modules over the string A plus. So that's a pretty strong descent result. In particular, notice that the plus boundedness condition only depends on the tilt, and that is crucial if you want to do anything on the Fargues-Fontaine curve. And so I'm running out of time, I guess, right? Yeah. So I will not say anything about the proof, sorry, but I will now state the corollary that's important to us. Namely, there is a unique hypercomplete sheaf on, well, now I can just take the category of all small b stacks in the sense of Schulze. So this includes all diamonds, and in particular all limited varieties over any field if you want. So for each of these things, I can now assign some infinity category, which I will just call, maybe let me just write the QP version out here, because in general, maybe one needs to be slightly careful. So this, say x, let's do d of x comma QP, such that if S star AA plus is plus bounded as a plus bounded perfector space in characteristic P, then this category DSQP is just the category of solid hat Quasicoherent sheaves on the Fargues-Fontaine curve over S. Okay, so on each perfected space, I have a very nice category I can work with. And this thing is literally just a normalitic space, and it's understood how to define solid sheaves on solid Quasicoherent sheaves on adic spaces. So this is a RAS category, and it has nice affine covers, and people have studied this a lot. So this category is relatively simple, but because I have this V-descent result, I now have a good category on each V-stack, in particular on each rigid variety, which hopefully, and I mean, from my experience, from my thesis, once I had the similar result here, but with a mod P version, once you have the descent result, the rest of the construction of the six-functor formalism is not that hard. Yeah, so that will be the next step for us. Then we have the six-functor formalism. Maybe let me make one remark. Maybe I'll just say it orally. So in my thesis, or maybe, okay, remark. My thesis, I constructed the category. I solved the same problem but with FP coefficients, and the answer there was to construct some category which I called O as plus mod pi, and then I took some fine variant modules over that. And we are pretty sure that this is actually the same as the category of solid almost modules on the relative Fargues-Fontaine curve, where I take here O plus mod P. Okay, so this basically this new construction really recovers what I did in my thesis, but it extends it because now we can talk. Okay, I didn't write plus here because I'm a bit worried about the plus on the Fargues-Fontaine curve. But apart from that, we have something now which recovers the thing in my thesis, but also now works over ZP and over QP and everything. Yeah, thanks a lot.
Is this final remark known? Because I think you said like we're pretty sure.
Well, we made some computations and it seemed to work. Well, the problem is that this thing, you need to be careful with defining this thing because the Fargues-Fontaine curve is not perfectoid, and hence O plus sheaves. There's no definition of Quasicoherent O plus sheaves on that thing. But you can just ad hoc define something. In the Fargues-Fontaine curve, you can write it as an increasing unit of affine stuff. And then on each affine stuff, you just take modules, and then you take the limit over these categories. And with that definition, I think this is the equality. Yes.
The D solid hat OXS thing, is that related to that? Shouldn't be related to that?
Yes.
Is that, I mean, is it literally that?
Well, except that this ring is adic and this one's not, right? So what you do is you take an affine in here. That is just some spar A plus. Then you apply this definition to the A plus. Then you invert P. I mean, this has Quasicoherent things, so I can just invert P in there. And I take modules over A inside of this category. That gives me a category on an affine, and then I glue. And the fact that these things has been shown, for example, by Andrej. Okay, maybe he didn't use the hat definition, but it doesn't matter. I mean, this doesn't matter here.
Yeah, I kind of want to ask the same question. I mean, if I just take A to be ZP, like, can you describe like the left-hand side in terms of things that I know? If I know what like.
Yeah, so that is A. Well, do you know this one?
Is that just P complete, or is this a solid sort of add some like weirder things?
Yeah, this has some weirder things. Yeah.
Okay, but even if so,
so if A is a finite type over ZP in some topological sense, then this is actually an equivalence. So we get nothing.
So for ZP it would be an equivalence.
For VP, this is just this. Yes.
Yeah, okay.
And then, yeah, what describing this? Well, I mean, I guess the easiest description in the case of ZP is, I can just me. But in this case, you can just write the generators as products.
Yeah.
So you basically just take these topological things and you take all columns of that and some condensed.
So it's more interesting for kind of crazy things, I guess. Sort of very simple.
I mean,
somehow doesn't.
I mean, the point of this is that they are defining Quasicoherent modules. I don't know if you want them to be interesting, but
No, but I'm just asking, like, what is the problem that it's sort of solving, right? So,
oh yeah.
So, finite over ZP, then
so
you
for
don't.
finite over ZP, I don't do anything.
Yeah.
Yeah, only the problem is this cohomology. I mean, this thing is p-complete. That's okay. Problem is this cohomology. Yeah. So I have to p-complete again.
Because I'm sort of in my idea somehow does someone start with p-adically complete generators and then so somehow so everything is kind of built out of p-adic.
But I don't just take the int completion of.
No, I mean, it would be.
Yeah, this thing is more complicated somehow.
But that seemed to be the point you were making. Somehow this differs from the other ones. P-adic complete generators.
Yes, I mean literally the definition of this is I take the compact generators of this.
Yeah.
I mean I take all compact objects in here. I take the p-completion of that.
Yeah.
Then I take everything I can build out of that using finite limits and colimits inside of this.
Finite.
Yeah, I mean just triangles.
Okay, yeah.
And then I take the incompletion of that.
Okay, yeah.
That's literally the definition.
Nice.
I mean it's kind of it feels a bit ad hoc, but it seems to work. So. Yeah.
I think a critical mass of us in the audience wants to know what descendability of index less than or equal to D means.
Okay.
I cannot answer one sentence. You cannot answer one sentence, I think. So does D solid A on everything?
Say again?
Like does D solid A, like the D solid head guy with A paired with A define an analytic ring structure?
No, because this is not what the case for. I mean, not in the sense of Clausen-Schulze at least. You could try to generalize the definition of analytic ring to include this. Right, but it doesn't embed, I mean, it does not embed into condensed A modules, as far as I know. So yeah, not in the sense of Clausen-Schulze, but I mean, I also thought a little bit about maybe there's a generalized definition of analytic rings that includes this one. Feels reasonable that at least this one can be made somehow into some formalism, but I mean, honestly, I don't care too much. It just works in the second. Okay, so you want to know what descendability of index 2 means? Or index something? Well, I can try to be quick. Okay, if I have the map F, then I can consider the functor tensoring over A solid with B solid. Or maybe solid hat or whatever. I mean, okay, maybe mod I. These things are mod I, so they're discrete. I can consider this functor, right? So this functor lives. I can view this as a functor from B solid A to D solid A, right? And what I can do now is I can take the category generated by that under finite colimits and limits. I guess, I mean, since it's stable, doesn't matter which one, retracts and composition. And so basically everything I can build out of infinitely many steps out of this functor. And descendability means, so at descendable, by definition means that this category contains the identity functor. Okay, so roughly what this is saying is that out of base change from A to B, infinitely many steps, I can build just the identity. And the point is these finitely many steps. Once I know I can build, basically I can recover anything out of the space change in finitely many steps. It's not so hard to see that you immediately get descent for a very strong reason. And okay, I still haven't explained what the index means, but you can look at, like, I mean, there's a canonical way of trying to find the identity in here. And okay, basically the index says how complicated is it to get the identity inside of this category, and maybe I'll just leave it at that. And if you want more details, ask me afterwards.
Okay, thank you.